Hello, I'm Abigail Spence, and this is Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet and compare our measurements to the distance dependence predicted by the equation for the on and off axis magnetic field derived from the Biot-Savart law. Concepts that will be discussed is magnetic field, magnetic dipole, Biot-Savart law, and distance dependence. My results by the end of the lab were a distance dependence of negative 2.3091 and a magnetic dipole moment of 2.35 ampere square meter. As I go through this lab, I will be discussing the first part of the experiment, including its data and calculations, the second part of the experiment with its data and lab observations, the code, model, and its comparison to the data, and lastly, some concluding questions. My experiment was conducted in Acworth, Georgia. In the first part of the lab, I had to use my phone as a magnetometer and locate a magnetometer chip. First, I oriented the magnet's magnetic field orthogonal to the Earth's magnetic field so they can be accounted for separately. Next, I moved my phone perpendicular over the meter stick until I found the max X component of the field and placed a tape at that spot on the phone. Next, I rotated the phone 90 degrees and slid the phone over the meter stick until a max Y value is found and added another tape along the phone at that location. The red X represents the location of the chip. Using the chip location as a measurement indicator, I had to find a distance from the magnet to the sensor that produced a magnetic field with an X component of magnitude 20 microteslas. I had to measure this distance twice to help control for human error. This process was repeated for the magnitude 70, 120, 170, and 220 microteslas in the X direction. Once all the data was collected and the R values and X magnetic components are averaged, the data is plotted and the graph is outputted with an equation y equals negative 2.3091 x minus 13.381. The distance dependence is the slope of this equation, negative 2.3091. Next, to calculate the magnetic dipole moment of the bar magnet, I solved for k in the magnitude of the magnetic field equation by doing e to the power of y-intercept. Then I took the same equation and set it equal to Biot-Savart's law equation. From there, I solved for magnetic moment. I then plugged in every average R value into the equation which outputted the corresponding dipole moment. Lastly, I took the average of those magnetic dipole moments and got my answer, 2.35. In part 2 of the experiment, I moved the phone to where the magnetic field is 100 microteslas, labeled as dperp. I then slid the phone perpendicularly along another perpendicular meter stick to the same dperp distance. From there, I recorded the Bx, By, and Bz values, a distance of d about 0.25 meters away from the bar magnet at a 45-degree angle. I did this 3 times to prevent error. Throughout the physical experiment, observations that were made were when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the X direction. Also, as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. Lastly, when the magnetometer is aligned on axis with the magnet, then the only source acting on the Y component of the magnetic field is the Earth's field. To create a digital representation of this lab, I edited the starter code. In the first set of code, I created a function for the magnetic field. I coded for the Biot-Savart law formula at the top of the screen on line 36. Then I rescaled the field vector and edited for each axis and perpendicular vector to account for all directions the magnetic field would spread out in. In the second set of code, I coded for the 2 axis arrows and the 4 perpendicular arrows that would show up in the model, calling for the magnetic field function and the scaling factor. Then on the third set of code, I coded for the arrow that represents the magnetic field in the 45-degree angle from the axis, similar to the code from the previous arrows. Once the code ran, it resulted in this model. The orange arrows are in axis, the cyan arrows are the ones located perpendicular to the bar magnet, and the pink arrow is the magnetic field 45 degrees away from the axis. It aligns similar to the orientation of the lab. Comparing the code magnetic field values to the experimental values, the experimental values are a bit bigger for the X and Y components, while a Z component also exists when there shouldn't be. These differences can be caused by error in phone orientation or error in location of the magnetometer chip, as well as effects from the Earth's magnetic field or other unknown objects in the surroundings with magnetic field. In conclusion, there are 2 follow-up questions that we have yet to answer. The first one is, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Well, the Earth's magnetic field would be superposed to the magnetic field of the magnet, and I would have not been able to measure them separately to account only for the bar magnet. I would not be able to tell how much of the magnetic field is due to either the bar magnet or the Earth. The second question is, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? If the magnets were attached north to south, the magnetic field would add together, or in other words, double, since the magnetic momentum would be doubled. If it were attached north to north or south to south, the magnetic fields would oppose each other. In the end, we have applied our knowledge of magnetic fields and Biot-Savart's law in order to find and understand distance dependence of magnetic moment dipole. Thank you.